Hello, I'm Jun Kim from Department of Mechanical Convergence Engineering at Hanyang University in Seoul. Today I'll be presenting of the topic of machine learning for identifying design changes of vehicle with wake flow. My advisor is Professor Simon Song, and this research was conducted in collaboration with Hyundai HV. During design vehicle, wind tunnel experiments are conducted to analyze the airflow, especially the wake flow, and we assessed its aerodynamic performance. Variations in design lead to different airflow patterns, allowing the identification of design influences. This process balances design and aerodynamic performance. However, inconsistencies in analysis due to evaluators' experiences pose a significant issue. So trial and error analysis is then utilized, increasing development time and cost. Fluid flow possesses complex high-dimensional and nonlinear properties, making standalone flow data analysis challenging. Similarly, AI excels in inspecting such characteristics from vast data volumes, and it finds applications across fields like fluid dynamics. Thus, I aim to address the consistency issue by creating an AI model to replace evaluator-based processes. To do this, input flow data and desired design influence outputs need to be defined. Here's the objectives of the research. This study aims to develop an AI model for identifying design change of vehicle with wake flow. In detail, I researched the best form of input wake data for effective training to predict the changes of vehicle design. Two output labeling methods were examined: multi-level classification with GradCam visualization and multi-target regression. Let's define the training data used for the model. I employed the data associated with the vehicle's design elements as the output data. Each vehicle comprises 15 design elements, and varying the sizes of these elements allowed us to generate a variety of vehicle shapes, leading to the preparation of 72 vehicles. Following this, velocity fields were acquired for input data through wind tunnel experiments. Since given data are symmetric and GradCam has to be symmetric too, I utilized the half of the wake fields. However, training an AI model with just 72 data is challenging. So I propose a strategy to augment the training data. My main focus is on the variations in wake patterns due to design element changes rather than the absolute values themselves. By selecting any two vehicles from 72, we can compare the design and wake data individually. This enables the use of wake comparison data as new input and design comparison data as new output. Consequently, this yields 2,556 data corresponding to the combinations of 72 choose 2. Additionally, I present 2 design comparison strategies and 3 wake comparison strategies. Next, I'll introduce the 2 design comparison strategies. The first is multi-level classification, which predicts multiple corresponding classes for input data at the same time. In the study, my aim is to identify changed design elements using provided wake comparison data. A design element with alteration between two vehicles receives level 1, otherwise 0. The second is multi-target regression, which predicts multiple numerical values. A goal is to estimate the normalized numerical differences in design elements between two vehicles. Next, I'll show the 3-way comparison strategies. The first involves using the main flow component differences, specifically the variation of UX, which has been utilized for evaluator-based analysis. The second is cosine similarity between two vorticity fields. A cosine similarity can quantify the similarity of patterns between two vector fields. For the third, similar to the second one, cosine similarity is calculated for the gradient vector fields of UX velocity components. For this data, Gradient effective fields of UX was drawn from a literature that suggests gradient of scalar function for effective edge filter detections in images. For model training, Resonant 18, a 4-mod residual neural network, was employed. Resonant is a convolutional neural network developed for image classification. It consists of residual blocks, as shown below, which contain a structure to incorporate input-output information. The Resonant 18 model was augmented with a final layer, producing 15 output values for design comparison. Training hyperparameters are as follows. Data was split into 7 to 3 for training and testing, respectively. Batch size was 20, with a learning rate of 0.003 for 500 epochs. Now I'll show the result from training using the multi-level classification approach across the 3 predefined input data types. Here, accuracy signifies the proportion of correctly predicting all 15 design element changes within the whole dataset. Comparing the red test accuracy lines on the graph, it's clear that using cosine similarity of vorticity produces the highest accuracy. Similarly, for the third case, accuracy surpasses 70%. What we can observe from this result is using velocity derivatives and cosine similarity, which normalize data from minus to 1, might enhance the model's predictions. Additionally, I utilized GradCam to visually explain the predictions of this classification model. GradCam visually represents a classification model's decisions on images by highlighting regions of interest based on the model's gradient values. For example, if the model identifies an original image as cat or dog, GradCam emphasizes the image's influential regions. You can see below a few GradCam results applied to our model. These results pertain to the model trained using cosine similarity of vorticity, particularly for design elements predicted as true positives. So we can visualize where the model focuses for decisions. For example, for design element number 1, we can compare the GradCam results and the actual location of this element. Next, similarly, I'll now show the results of training the model using multi-target regression with the same input data. Accuracy was assessed through Bayes correlation coefficients between predicted and actual values of the 15 design element differences. These coefficients were averaged for an arithmetic mean. Just like the multi-level classification results, a successful training was noted with higher accuracy using cosine similarity, particularly that of vorticity. Furthermore, we evaluated the individual design element prediction performance through 15 graphs, plotting ground truth against predicted values across all test instances. Each point represents a single test data point, and the closer to the y equal to x line, the more accurate predictions. The colors of the points indicate data density. Given coefficients of 0.86 or higher, and the colors of these points, we can confidently conclude accurate predictions for each element. In conclusion, we developed an AI model for analyzing and predicting the effect of vehicle design changes on the wake flow. So we trained the Resonant 18 model using wake and design comparison data. Consequently, the most effective input data is the cosine similarity of vorticity fields, which achieves a maximum accuracy of 75.1% for multi-level classification and maximum averaged Pearson correlation coefficients of 0.9445. Here's what I prepared for today. Thank you for listening.